the peak is moving off to the left, which means it's going to be especially tall in that region. Now the sun is somewhere right between these 5,000 and 6,000s. So yeah, I mean, it's in the red if it were cooler than the sun. The sun is, like I said, about 5,500, somewhere in there. So the sun gives off most of its light in kind of the yellowish green region. We don't perceive the green because it's scattered away by our atmosphere and our eyes don't pick it up very well. But Macargo is beyond that. So his peak is going to be way off to the very edge of the visible, which means it's going to be really high in that ultraviolet region, meaning you're going to get a lot. But we want to know just how much, because just saying, yeah, it's a lot, that's no fun. We want to know how bad this is going to suck. So we got this equation that describes everything. It tells you the intensity for a given temperature. It has a whole bunch of constants in it. But I can pick the temperature from Macargo. I can use calculus to integrate that, which I will spare you. But I want to do that between 315 nanometers and 280, which is the range for the ultraviolet B, which is the part that gives you the sunburn. So if I do that integration, I get for Macargo, he gives off 6.44 times 10 to the 23rd watts per meter per steradian, which is weird units. The watts makes a lot of sense. Watts is a unit of energy, so you're getting energy from it, which is what we'd expect. Meters squared works perfectly because you have a surface area, being kind of looking straight on, that's going to be what's getting the radiation. The weird one is this steradians thing that no one understands because only idiots use a spherical coordinate system like this. It works great in astronomy because, you know, we live in a giant celestial sphere. But in most things, you wouldn't want to use it. The idea of it is kind of like you had a chunk through a block, but this one, since it's spherical, it grows. It's like a wedge. But same thing for the sun. We can do that, and we get 2.15 times 10 to the 22 watts per meter squared per steradian. But straight off, this isn't looking too bad. I mean, yeah, our order of magnitude here, it's like 10 times as much. Okay, so if I burn in 10 minutes, that means Macargo gives me a burn in 1. What's so bad about that? I just keep him in the Pokeball. Never let the bastard out. I captured him. What do you want? He's in my Pokedex. I'm not using him to fight. I'm pasty and white. There's a couple other problems, though. First off, the sun is really, really, really far away. 93 million miles. In other words, it's going to spread all that light out. So even though it gives off a lot, you're only getting a small amount of it. But the other thing is, the sun is also really, really big, which means it has a lot more surface area to be given all this ultraviolet off from. So these two effects are going to kind of cancel each other out, but we want to figure out which one's going to win out. So if I put in the units and everything, multiply it together, doing the same thing for Macargo, being 10 meters away, I get that he's going to give off 3.22 times 10 to the 21st watts. And meanwhile, the sun, the amount you're going to receive is 2.94 times 10 to the 15. So the difference between the two just jumped from about factor 10 to a factor of about 100,000. Much, much worse all of a sudden. 10 minutes now to like a half of a second or even less. So yeah, I don't even want to get near enough to capture him. But there's more that's actually kind of worse. We have an atmosphere that protects us from 98% of the sun's ultraviolet, which means on that last figure for the sun, we need to reduce that by another 98%. In doing that, we're going to get what's left over, that 0.03, and when we divide that out, we get that Macargo gives off 36,000 times as much ultraviolet, or that's how much more you get hit by. In other words, if you're pasty and white like me, and you sunburn in 10 minutes, you now burn in a nanosecond. Do not add that one to your catch-em-all list. Staying on the topic of Pokeballs, you over here, somebody was earlier, it's like, I have a Pokeball, and then you open it up and go, nothing's in it, and I promised you that I would show you that's a darn good thing. Question is, what's up with the Pokeballs? So, I don't really get them. They hit the Pokemon turns all glowy, kind of turns into this wiggly light beam and teleports into it or something. So how does this really work? Well, there's two things that you can notice about this first off. First of all, the Pokemon doesn't have a cohesive form. He's not still just like a miniature Pikachu inside the Pokeball. No, he's been all wigglyfied to turn into the light beam, and he's not still a Pikachu. It's completely not even the right shape. Doesn't work there, all right? Also, he can't have mass. Brock is the rock guy. He has like onyxes sitting on his Pokeball, and they're like supposed to be 500 pounds. You're telling me he's walking around with 500 Pokeball on his belt? No. They've somehow gotten rid of the mass by the time they're in the Pokeball. So there's only two ways I can even begin to approach Pokeball working. We could disassemble the Pokemon, just like pull every single atom apart. Ow. That would take care of the first one. He wouldn't have the cohesive form, but also it doesn't satisfy the second one. If the atoms are still there, they still have mass. So we can't actually do just breaking the Pokemon up. The thing we can do is conserve or convert it to energy. That's great because it'll go ahead and take care of the first one. It doesn't have a cohesive form. But it also, if it's no longer mass, solves that problem. So we can go ahead and let's talk about Pikachu because he's quintessential. He has a mass of 5.9 kilograms, so just over 10 pounds, about 13 actually. The radius of the Pokeball, which we're going to use in a minute, is about 2 inches. And if you use that with a volume for a sphere, you can get that there's 5.2 times 10 to the negative 4th cubic meters in there. The problem with this is that when you convert mass to energy, you get a lot more energy than you had mass. And I'm pretty sure everyone knows E equals mc squared thing. So let's use it. We got the mass of Pikachu, c is the speed of light, multiply it together, and Pikachu's worth 1.7 times 10 to the 9th joules. So 1.7 billion joules. Yay, what's a joule? What's it going to do? Well, let's take that amount of energy and divide it amongst all the molecules of air in the Pokeball. A normal cubic meter of air has 3.4 times 10 to the 25th, but since the Pokeball was smaller, it's only 1.8 times 10 to the 22. Divide the amount of energy, that joules, by that amount, and then put it into this formula. So how much energy does each little particle have, each molecule of air? And then this formula will tell you what the temperature is going to be. It was a lot of energy. It turns out that if you do that, solving for T, you get 4.8 times 10 to the 9th degrees Kelvin. Who works with Kelvin? No one besides losers like me. So it's about 8.6 billion degrees Fahrenheit. That's a wee bit hotter than the cargo. Putting it into perspective, temperature of a blowtorch is about 2,000 degrees Kelvin. Surface of the sun, we worked with that earlier, about 6,000. Oh, you know, the nice cool atomic bombs. 30,000. Temperature of the core of the sun, where it's taking hydrogen and fusing it into helium, is 1.6 times 10 to the 7th. The temperature necessary to fuse oxygen in really high mass stars, 1.5 billion. I skipped one. Oops. Temperature of a supernova, 1.0 times 10 to the 11th. Where does he fit? A little bit less than a supernova. But notice what comes right before it. Temperature necessary to fuse oxygen. What is 20% of our atmosphere composed of? Oxygen. You catch a Pikachu, you ignite fusion in our atmosphere and destroy the world. So, I am quite glad that you have nothing in that Pokeball. So, I think we're just about out of time now. Oh no, I've actually got... Wow, how did I breeze through that so fast? Electricity is a form of energy. Since I got some extra time, I'm going to jump over to another version of the panel here and go through a couple more. Everyone having fun? Yeah! How many people have been to these panels previously?
Not this one.
Oh, wow. All right, let's pop this one up. This was last week at AFW. They gave me an hour and a half, so I had a little bit more time, stuck some more in. So one of the ones I'm thinking about for next year is I was starting to look at like internet memes, and for whatever reason, Cat jumped into my head. And I'm thinking about talking about the physics of a toaster strudel as rainbows chasing him. Pop-Tart is a toaster strudel. Same idea. Whatever. All right, another topic that no one gets right in anime is anytime anything falls. Yeah. I didn't bring speakers because I didn't plan on doing any segments that needed it, but this is from Final Fantasy VII Advent Children. So Sephiroth and Cloud are fighting on the top of the building. They chop out this huge slab from underneath them, and they're falling down, walking around on these huge falling chunks, having their epic sword fight with fantastic music and Bishonen.
Yes!
So they're just walking around, jumping off these things.
Use one of the other mics.
That's the best scene.
Alright, so the question is, what's wrong with that? I mean, there's I'm sure a lot wrong with it, but it's a very dense little clip there. I mean, there's so much sword fighting, falling stuff, flashy camera angles, and Bishonen, that I'm sure most people couldn't pick out all the science. So let me simplify it. I put together my own animation to pick out the important parts here. So one day, Bowser kidnaps Luigi. Mario rushes onto the scene to save the day, but Bowser flies off in the sky. Fortunately, bars start falling from the sky. Mario hops up them and saves the day. Alright, so what's going on here? I mean, everyone's played Mario. Mario's totally legit. Well, whenever anything is falling, there's two main things going on. You have a force acting downwards, which is the force of gravity. And thanks to Newton, we know that any force can be described as its mass times its acceleration, which is, as I've drawn it here, ma. I'm going to switch out a in a little bit to call it g because it's the force of g for gravity. But opposing that force is the resistive force of air friction. And this is going to be also composed of its mass. It's going to be dealing with how fast it's going, so we're going to toss velocity in there. And it's also going to depend on some constant k, which has to do with how viscous whatever it's falling through is. If you're falling through air, you can fall pretty easily. You fall through water, not so easy. You fall through molasses syrup, you're not really falling much. So this is what's going on with the idea of all this. And now we need to put that all together. What we want to figure out is how things are going to fall for a given time. What's the velocity going to be? So let's figure out how this all works together and solve that using calculus. They used to put this panel on Sunday mornings. They don't do that anymore. Alright, so what I do is I take the two forces, and you always can add any forces together to get the net force on a system. So we have it, the force is equal to negative mg, which is the gravitational force, negative since it's going downwards. We have negative kmv, I'm making it again negative because it's resistive. And then I set it equal to, as we said before, mass times acceleration, except because we're doing the calculus thing here and now everyone walks away. I use dv/dt. Specifying that kmv has to be greater than 0 because you can't have a resistive force that's helping you along. That just doesn't make sense. I factor out the negative m here, and then I notice there's an L on both sides, so I can just cancel that out. And that's the first thing to really notice about this. The mass is canceled out of this equation, so it doesn't matter what your mass is. If you're Cloud, Sephiroth, or the giant freaking block of concrete that's falling, you're going to fall the same way. So it's going to go through all this. And what I really want to get to is this part down here, which still looks horrible and nasty, but it's not nearly as bad as you'd think. So we want to talk about, as I said, the velocity at any given time, and all this stuff looks scary, but most of it's actually constants. E is a number, 2.71. K, we said, was the constant of how to look at the viscosity of your fluid. T is the variable we're concerned about, so we leave that as a variable. K is a constant, C was a C for constant from integration, K is a constant, G is the gravitational constant acceleration, K is a constant. So all of this, except for T, is constant. I could plug in the numbers and just simplify it like a lot of people like to do, but we don't really even need to do that to understand what's going on. If t is really small, this part, the negative kt here, is important. But if kt gets really, really big, this negative kt gets way bigger than this whole kc thing, so kc we can just ignore. Also, it's a negative in the exponent, which those that have taken algebra knows that that means you take the reciprocal. So really, this whole thing should be down here in the denominator, and if t's getting really big, it's making something really big in the denominator. And if you put something really big in the denominator, it just goes to 0. This whole term is gone, and all we really care about when t gets big is this, g over k, which is a constant. So if we graph that up, here's what it's actually saying. You start off with this term being important, but it levels off because it approaches a constant. And this is the idea of terminal velocity, that thing you don't talk about at airports. The thing to know about this is, as I said earlier, the mass is irrelevant here. So if something starts falling, anything else